To get the best picture of the electron distribution of any compound, we cannot just stick to inductive effects. We again have to look at other electronic effects, including resonance. So in this case, let's go back to our analysis of our compounds and trying to see which one has the most electron poor carbonyl carbon and, well, the most electron rich or the least electron poor one. Again, let's review our analysis of methanol. So we started off with our methanol or formaldehyde molecule. We decided to push a pi bond up to oxygen, creating the resonance form, which I'll put below, showing that our carbonyl carbon is positive and our oxygen is negative, at least partially. And for all of these, since they all contain that carbonyl carbon functional group, they can all exhibit the same kind of resonance structure. We can all push a pi bond up to that oxygen, which we can color code red, creating their different resonance structures, all of which show a carbonyl carbon that is positive. Oops, so make sure you enclose all of your resonance structures in square brackets. So we can draw it there. Let's put this oxygen there. Oops. So to negative oxygen, positive carbon, pi bond, pi bond, pi bond. Now, right now, the presence of other pi bonds in phenylethanone can already give us a hint that it will have several other resonance structures. So let's take a look. Let's color code the other pi bonds. Perhaps we can turn this into a blue one, this into a green, and this one into a red. Our goal is to show or try to see if the positive charge can be spread out through resonance structure. And one of the moves we can do is we can take this blue pi bond and push it to become another pi bond on a carbon beside it, on the carbon where the positive charge is at. In doing so, okay, we now transferred it here. The oxygen is still negative. Red pi bond is still there. Green pi bond is still there. And now the positive charge, okay, will be on this carbon that only has 3 bonds. We can then repeat the same process again and again. So let's take this green pi bond, turn it and transfer it to the carbon or towards the carbon where the positive charge is. And in doing so, you will end up with a structure that looks like this. Okay, we've transferred it there, and the hydrogen is still there. This carbon over here will only have 3 bonds left, and therefore will be the one that is positive. And then we can do the same thing with the red pi bond. We can transfer it towards the carbon where the positive charge is now transferred, or is now located rather. And where it was once located, we'll have the positive charge there. And then if we move the blue pi bond back into the ring, the positive charge ends up back on the carbonyl carbon. And so the cycle has ended. Now let's look at propan-2-one. Will propan-2-one have any other resonance structures? Beside the carbonyl carbon with a positive charge are two CH3 groups, and both of these are sp3 carbons. No pi bonds, no lone pairs to resonate, and therefore we cannot resonate anymore. And obviously, going back to methanol, beside the positive carbon are two hydrogens which cannot participate in in resonance or pi bonding. Yes. With that, okay, we can show that the carbonyl carbon for all does in fact have some positive character, but for phenylethane 1-one, that positive character of our carbonyl carbon is only one instance or out of how many more possible resonance forms, meaning that positive charge is further spread out into that benzene ring or pi system. Okay? That makes this carbonyl carbon a lot less positive than the others because we've spread pi electrons towards that carbonyl carbon. Whereas the partial positive charge in methanol and propan-2-one are localized in place.